Let's talk a little bit about congruence and look at one more construction before we start to look at some proofs. So let's start by constructing an isosceles triangle that is not equilateral. So let's think about what this triangle will need to have. Since it's not equilateral, it cannot have three congruent sides, but it is isosceles, so it will have to have two congruent sides and one side that's not congruent to the other two sides. So let's start by drawing that side that is not going to be congruent to the other two. We can make it any length we want to. We're just going to make sure that the other two sides that we draw are not congruent to this side. So let's say that is the side that will not be congruent to the other two. Now we're going to take the compass and I'm going to measure the length of this side. Now if I wanted an equilateral triangle, I'd want to keep that measurement. But I don't. I want an isosceles triangle that's not equilateral. So I'm going to stretch this compass out farther than that and make a decision that that is how long the other two sides of this isosceles triangle are going to be. So now we need to find that third vertex on the triangle. So we'll bring the compass up and make an arc up here. And through that arc there will be a point that is the third vertex of the triangle. Now we'll flip the compass over, put the point of the compass on the other side of the line segment, and then make another arc that crosses the first one that we did. Now that point of intersection is going to be where the other vertex of the triangle is. So now that we've got the vertices of this triangle defined, all we have to do is bring our straight edge in and complete the construction by making our last two sides of our triangle. Now just a reminder of something we said with other constructions as well. Remember that even though we may be using some tool that has some marks on it, like this ruler has got some marks for inches and for centimeters, we don't measure with those marks. Measuring in constructions means we use our compass to measure a distance and then use that measurement in order to make sure that we have the same distance from one point to another point. So now let's look at one more triangle congruence theorem, which is called angle-angle side. This theorem says that if two angles and a side opposite one of those angles of one triangle are congruent to the two corresponding angles and the corresponding side of another triangle, then the two triangles will be congruent. Now that's four triangle congruence theorems we've talked about. Side, 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 angle, side, angle, side, angle, and now we have angle, angle, side. We can use any of these theorems to prove that two triangles are congruent. But is there an angle side side theorem? Well, let's take a look at an example to see whether or not we can construct a unique triangle if we know an angle and a side that's adjacent to that angle and a side that's opposite that angle. So suppose we have this angle and these two sides, and we want to construct a triangle out of that. So we're going to see if we can construct two triangles that have to be congruent with these parts. So there's the angle that's congruent in both of those triangles. We need a side that's adjacent to that angle that's congruent, so we've got that. And now we would need a side opposite the angle that's congruent in both triangles. So the question is, if we put that last side on this triangle that would have one vertex at B, would we necessarily have congruent triangles? And as it turns out, not necessarily. If you look at these two triangles, they both have a congruent angle. They both have a congruent side that's adjacent to that angle. That's the one that's marked with 2 tick marks. And they both have a congruent side opposite that angle. That's the side that is marked with 1 tick mark. But the two triangles definitely are not congruent. So there is no such thing as an angle side-side theorem for proving that two triangles are congruent. So let's take a look at some proofs now. We have an isosceles triangle here, ABC, and we're told that segment AD is the perpendicular bisector of side BC. And we want to prove that segment AD bisects angle BAC. When we write proofs, we're going to do 2-column proofs. The first column will have a statement in it, and the second column will have a reason for saying that statement. When we make a proof, the first statement that we have in our proof will always be something that was told to us in the problem. It will be something that was given to us. And the last statement in our proof will always be what we're trying to prove. So we need to look at this picture and decide what was given to us. Well, certainly we were told that triangle ABC is isosceles, and because that was something that was given to us, the reason for that is that it was given. Now we were also told that segment AD is the perpendicular bisector of side BC. So that means we were told that segment AD is perpendicular to segment BC. And because we were told that segment AD is perpendicular to side BC, we can say that the measure of angle BDA and the measure of angle CDA would both have to be 90-degree angles. And that's because we were told that these are perpendicular, that we have a perpendicular bisector of side BC. So the definition of perpendicular is that those angles have to be 90-degree angles. Segment BD has to be congruent to segment CD. We were told that we have a perpendicular bisector, and by definition, because segment AD is the bisector of segment BC, segment BD and segment CD must be congruent. Segment AD has to be congruent to itself. That's called the reflexive property. Now we can conclude that triangle ABD and triangle ACD are congruent. And we're using the side angle side theorem for that. We have in each of these two triangles two corresponding sides that are congruent. We have an angle that's congruent, and then we have a third part of that, which is the next side that's congruent. And now that we have two triangles that we've stated are congruent, we can say that angle BAD and angle CAD have to be congruent because they're corresponding parts of those congruent triangles. And remember, we said we're going to abbreviate the phrase corresponding parts of congruent triangles are congruent with the letter CPCTC. And because these two angles are congruent and they make up angle BAC together, we can conclude that segment AD must bisect angle BAC because that's the definition of an angle bisector. A bisector is a segment that breaks an angle up into two congruent parts. So we've proven what we were asked to prove. Let's try another proof. We've got a picture that has some things marked in it as being right angles, and we have a statement underneath the picture that two line segments are congruent. And what we want to prove is that line segment AF is congruent to line segment BF. Now within this picture, it's going to be helpful to notice that we do have two triangles, and well, we have more than two triangles, but we do have two triangles that contain right angles, and we will be able to show that those two are congruent. And if those two triangles are congruent, then we'll be able to say that their corresponding parts are congruent. So let's start with our first statement. Now remember, the first statement is always going to have something to do with information that was given to you. And in this case, segment DF and segment EF are congruent because that was a statement that was just given to us within the picture. We can also say that angle BDF and angle AEF are congruent because within the picture they're both marked as being right angles, so that's considered given. Angle F is congruent to itself. That's the reflexive property. And now we can conclude that triangle BDF and triangle AEF are congruent. The congruence theorem we're using this time is angle side angle. We have two congruent angles, and then an included side, and then another angle on the two triangles that are congruent. And finally, we can state what we're trying to prove, which is that segment AF and segment BF have to be congruent, and that's because they are corresponding parts of the congruent triangles. So this time what we're given is a parallelogram, and we want to prove that angle BAD and angle ADC are supplementary. Now the only thing that's been given to us is the picture and the fact that we were told that this is a parallelogram. So we can certainly make that our first statement, that we were given a parallelogram. We can also say that segment AB and segment DC must be parallel, because if this is a parallelogram, then by definition the opposite sides have to be parallel. Now we're going to do something to the picture to help us see the next step. Let's extend segment AD and show the line that contains that segment. And let's mark an angle in the picture. We'll call it angle 1. So our next statement is that angle 1 has to be congruent to angle ADC. And what's important to notice in this case is that we do have parallel lines or parallel line segments. And we've stated that segment AB and segment DC are parallel. So we have those parallel lines that are cut by a transversal. The transversal is that red line that we use to extend segment AD. So we know that if parallel lines are cut by a transversal, then we have lots of congruent angles. And in this case, angle 1 and angle ADC would be considered corresponding angles, so they must be congruent. So now we can say that angle 1 and angle DAB have to have a relationship to each other. Because we have this straight line that we drew, we can also look at the straight angle that's created with angle 1 and angle DAB. So since those two angles together make up a straight angle, the sum of their measures has to be 180. So we can take the last two statements and put them together algebraically to say that the measure of angle ADC plus the measure of angle DAB has to be 180. The substitution would be to take the statement that says the measure of angle 1 and the measure of angle DAB equals 180 and put that together with the statement above it that angle 1 and angle ADC are congruent. So we're substituting the measure of angle 1 with the measure of angle ADC because those two angles are congruent. And finally, we can state that angle ADC and angle BAD are supplementary, and that's because in the statement above we said that the sum of those angle measures is 180 degrees, and by definition, if two angles sum to 180 degrees, if their measures do, then they have to be supplementary. So that's the beginning of our look at some proofs, and we'll look at a few more proofs later on as well.